Hello, everybody. This is John Public Man live. So we got the AP Calculus BC exam tomorrow. So I'm cramming in the rest of the units. This is uh, Unit 10. I said units, I mean just Unit 10, so the series and stuff like that. I'm going to be using the Algebras video. So before I start, I'm just going to need a little second to get prepped, so I'll be right back. All right, let's get right into this. So let's start. I'm on Unit 6 right now, so that's where we're going to start because I need to cram all this in. I actually haven't learned this yet. This is going to be a first for me. So let's go right into it. Hopefully I can just help you guys out. So this is the algebras I'm watching, so I don't know if I have to give them the credit or anything because it's not my video. It's their video, but it's Mr. Bean, and it's really funny. So let's go right into it.
Hello, Calc kids! Welcome back to another lesson in calculus. This is Mr. Bean, and today we're going to talk about some comparison tests for convergence. There's two different types of comparison tests we're going to look at today, and we're going to use these when we're faced with trying to figure out the convergence or divergence of a series that just looks really complicated. So what we do is we compare it to something that is easier, something we already have learned about figuring out convergence, like a geometric or a p-series, something like that. So here's first thing that you have to learn. If you have two different series and we say that a of n is smaller than b of n for all of n, then what happens is if b of n converges, then a of n also converges. Now this is kind of hard to just memorize, so let me show you just a little picture, and I think this will make a lot more sense. Draw really quickly for this one. Draw if you have some type of function that's going like this, and you can see here it's going to start flattening out, kind of like I should have drawn it like that. It's flattening out like an exponential decay graph. This is going to converge. So we'll call this one b of n. This is the larger one. So then underneath it, if I have a of n and it's going like this, and then it's starting to get squeezed underneath this, this one is our a of n. Well, if a of n is smaller than b of n, it's underneath the b of n, and we know b of n is converging, then a sub n also has to converge. That's what this means. If the larger one is converging, the one underneath it
That
must
makes sense,
also
sort of.
converge. So usually the picture helps you understand that a little bit more. So let's do that with the next one. If a of n is diverging, so let's say I have my a of n and it's going off forever to infinity, something like that. So this is my a sub n. Then the one that's above it, which is b of n, if it's going like this, if I know it's above it, it's not going to cross it. So when it gets there, it has to start going up. Then that means that b of n, so I'll call that one b, I should say b sub n, b sub n is also diverging. So if the lower one is diverging, then the one above it obviously has to stay above it, so it is also diverging. that's what this means. That's called the comparison test. And again, I would think of it like graphs. The one that's above it, if it's converging, then the one underneath it must converge. If the one below it is diverging, the one above it must also diverge. That's what these two statements mean. All right, let's put it into practice. Let's try this out here.
All right, let's see.
So what we
here.
have to do is find an example of something that we can compare it to. So I'm going to take this thing and I want to compare it to, I'm going to compare 1 over 2 to the n. See, these two things look very similar. Now, which one of these is larger? I'm going to remind you something right down here in the corner. If I have the fraction 1/10 and the fraction 1/2, which one is larger? 1/2 is larger, right? Half is much larger than a tenth. So the number on bottom, if the number is larger on bottom in the denominator, then the whole fraction is smaller, right? If this is bigger, then the whole fraction is smaller. So look at this. This fraction has a larger denominator, which means the entire fraction is smaller. So I can say this. I can say that 0 is less than 1 over 3 plus 2 to the n, which is less than 1 over 2 to the n. So it goes in this order. Now, what do I know about 1 over 2 to the n? This thing is geometric. So it's geometric, and I know that it converges from our practice with geometric series. So that means if this one is the larger one and it's converging, then this thing must also converge. So that thing I can say converges. Why? Because comparison test. Now, if this thing that I was comparing, if this diverged, if this thing was diverging, then I could not make any conclusion about this. So you have to be careful about that. There would be no conclusion if this thing diverged. I would have to come up with something else to compare it to. All right, so let's do this one. So here, the most obvious, based on the first example that we did, the most obvious thing would be to compare it to 1 over 4 to the n. But there is a subtraction here. So when you start listing in order which one is larger and which one is not, you'd have this 1 over 4 to the n is actually smaller than this whole fraction, 1 over 4 to the n minus 3, right? Because if you're subtracting 3, that means this denominator is smaller, which means the whole fraction is larger than 1 over 4 to the n. So now, even though we know this thing is, this is a geometric and it converges, so we know that thing's geometric, it converges. So even though we know this thing converges, we can't make any conclusion about this. We don't know what's happening. The lower one converges doesn't mean the one on top has to converge. It might still diverge. So what we do is we have to come up with something else to compare it to. So let's compare 1 over 3 to the n, because now I can say 1 over 3 to the n is actually going to be larger than the 4 to the n, right? Because if it's a smaller denominator, then the whole fraction is actually larger. So this now is 4 to the n minus 3, less than 1 over 3 to the n. And now I know that this converges, so this thing converges. And if the one that's larger converges, then that one must also converge. Let's do one more example of these. And that is when you have, let's see, you've got one that's not
I need to go back to that.
Larger converges, then that one must also converge.
Okay, wait. So if 0 is less than a to the n is less than b to the n. So this is b to the n. Or b of n. This is b of n. This is a of n. A of n is less than b of n. So if b of n converges, wait, this is confusing. Okay, let me go through my notes real quick. I'll be right back. Okay. So if we go back here, 5 minutes, 23 seconds. If b of n converges, then a of n. And a of n is less than b of n. So we need to find a function less that converges. Yeah, because if b of n converges, a of n can't has to be below it and converge. Okay, but if it's reversed, we can't say anything about it. All right, so let's go. So because 1 over 3 to the n, that's less. Oh, no, that's greater than that. Oh, because, wait. It's a smaller denominator, so it's greater. Okay, just like in this. 1/2 is greater. So if this converges, that has to
Also
converge.
converge.
And this does
Let's
because
do
the common ratio in this is 1/3. Okay, that makes sense. The common ratio is 1/3. So this converges by the geometric convergence, just like this one, and that
one
converges.
more
All right,
sample
I
of
got
these.
I got it.
And that is when you have, let's see, you've got one that's not exponential. So you have this thing here. Let's think about what can we compare. It looks kind of similar to this. I could compare it to 1 over 7n squared. I could put the 7 here, but I don't have to. I could just say n squared. I'm just trying to, the 7 won't really make much difference when you're talking about going off to infinity. And this here is a p series. So this is a p series, and the p is larger than 1. It's a 2. So therefore, this converges. So I know that this thing converges. So now let's compare them. So let's put them in order to make sure that we know which one's which. We got more stuff going on here in the denominator. The denominator is larger, which means the whole fraction is smaller. And then this would be less than or equal to the one we're comparing it to. So since this works, and we know that converges, then this one also converges. All right, so we've covered the comparison test. Now, next up, we're going to take a look at what's called the limit. The comparison.
Yeah, let me just think about that for a second. 1 over. Yeah, this greater denominator, so that means this is a bigger function. Okay, got it.
Test. Now, next up, we're going to take a look at what's called the limit comparison test. Now, I will admit, most of the problems I work through, I tend to use the limit comparison test. I just think it's a little easier, only because you don't have to figure out if A or B is larger. Which one's larger? All they have to do is both be positive.
That's really good.
And then you can work with it. See, on this other one that we worked
valid.
through, we had to know that the A was smaller than the B. One of the series, we have to know which one's larger and which one's smaller to make the comparison test work. So you will have problems that you have to work with that, but I find it a little easier to usually use the limit comparison test. So here's what happens. You don't have to know which one's larger. You just put them in a little fraction. So you set this up, and then you take the limit as n approaches infinity. So you put one over the other, and then as long as your limit exists, so your limit is finite, it exists, and it's positive, then what happens is both of these two series either both converge or they both diverge. So if you know the one you're going to compare it to, and then you take the limit, if the one you're comparing it to converges, then they both converge. If the one you're comparing it to diverges, then they both diverge. Okay, so it's a bit different than the other one where you had to know which one was smaller and which one's larger, and then that depended the convergence or divergence depending on which one was on bottom or top. Okay, so this is going to be a bit different. So let's take an example with this one. So how do you know what
Not
to
gonna
compare
lie, I
it
wasn't
to?
paying attention,
Be a
so
bit
let's go
different.
back.
So let's take an example. When you're comparing it to converges, then they both converge. If the one you're comparing it to diverges, then they both diverge. Okay, so it's a bit different than series. So you put one over the other, and then as long as your limit exists, so your limit is finite, it exists, and it's positive, then what happens is both of these two series either both converge or they both diverge. So if you know the one you're going to compare it to, and then you take the limit, if the one you're comparing it to converges, then they both converge. If the one you're comparing it to diverges, then they both diverge. Okay, so it's a bit different than the other one where you had to know which one was smaller and which one's larger, and then that depended the convergence or divergence depending on which one was on bottom or top. Okay, so this is going to be a bit different. So let's take an example with this one. So how do you know what to compare it to? So when you have something crazy like this, here I'm going to put this in quotation marks, this idea of reducing. It's not really technically reducing, but you have to think of this like horizontal asymptotes. If you were to go off forever and ever and ever, what would you really focus in on? You're focused really just on the terms that are the largest terms, this term and this term. So I'm going to take this thing and just kind of reduce it down. So I'm going to compare it to, so this becomes,
Oh, I see. So that's a over b, so it's
over
already
5n cubed, like
okay.
that.
I get it now.
But
So then
really,
you have to
I
set
don't
the
even need
limit.
the 2/5. I could just say 1 over n cubed. I don't even need the numbers there. So this is what I mean by quotation marks reduce, air quotes I'm doing, but you can't see me. And that is that you just reduce the largest terms to kind of figure out what you can compare it to. So now we have this thing, this 1 over n to the third. You could also do 2/5, 2 over 5 n to the third, but again, it's not necessary. You can just do this one. So now, does this converge or diverge? This is a p series, and it converges. Okay, so we know that this thing converges. So now let's set up our limit. So we're going to say the limit as n approaches infinity. And what we do, if you look back here, we're going to set up one of them over the other. So I just start with the one that was the one that they gave us. So the limit of 2n squared minus 2 all over this thing, 5n to the fifth plus 3n plus 1. And now we're going to divide it by the one we're comparing it to, which was this one right here. So we're, instead of dividing though, let's just multiply by the reciprocal, because that's much easier than dividing fractions. Multiply by the reciprocal. So that now gives us the limit as n approaches infinity of the n cubed distributes. That gives us this new fraction. And then that whole thing equals, remember your horizontal asymptotes, you're only worried about the n to the fifth. None of this stuff matters, right? You're going off to infinity, so blah, 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 blah. We don't even care about it. So it's just 2/5. Now, it's not necessarily that we care that the answer is 2/5. It's just that we care that the limit existed, that the limit is finite and it's positive. And so since it works, since it is finite and it's positive, then what we know is that this convergence is the same as this convergence. So since this one converged, they both must converge.
Okay, but he
so
got
our
this
answer
from
is
the original
that our
function.
original series converges. Sometimes in my answer key, I might have put both converges, but it's the same thing. You know, we're just saying if they both converge, then this one is obviously converging as well.
So he got that 1/3 and of 1 over
n. So this becomes, I could say 2
got that
over
from the original
5n cubed, like that. But really, I don't even need the 2/5. I could just say 1 over n cubed. I don't even need the numbers there. So this is what I mean by quotation marks reduce. Air quotes I'm doing, but you can't see me. And that is that you just reduce the largest terms to kind of figure out what you can compare it to. So now we have this thing, this 1 over n to the third. You could also do 2/5, 2 over 5 n to the third, but again, it's not necessary. You can just do this one. So now, does this converge or diverge? This is a p series, and it converges. Okay, so we know that this thing converges. So now let's set up our limit. So we're going to say the limit as n approaches infinity. And what we do, if you look back here, we're going to set up one of them over the other. So I just start with the one that was the one that they gave us. So the limit of 2n squared minus 2 all over this thing, 5n to the fifth plus 3n plus 1. And now we're going to divide it by the one we're comparing it to, which was this one right here. So we're, instead of dividing though, let's just multiply asymptotes, and it's positive. And so since it works, since it is finite and it's positive, then what we know is that this convergence is the same as this convergence. So since this one converged, they both must converge. So our answer is that our original series converges. Sometimes in my answer key, I might have put both converges, but it's the same thing. You know, we're just saying if they both converge, then this one is obviously converging as well. Okay, so that is how the limit comparison test is. Don't be confused with the comparison test, which we did the first one. So let's look at this one now. So we're going to use some type of reduced comparison. So let's compare what's something that would be reduced from this. Well, we just are going to look at this largest term, and I can get rid of the 5 there. Let's just do 1 over n squared. That's all we need to use to compare. Now, is this, before we start working it, we need to know if this converges or diverges. This is a p series. I don't know how to, I actually started spelling p, sorry. P series, and the p is greater than, I actually started spelling p, sorry. P series, and the p is greater than 1, so that, therefore this thing converges. See, what's nice about these tests is you get really good at the stuff we've already been practicing in Unit 10. The geometric series, the p series, the nth term test, you got to know all that stuff to be able to do these correctly. So you get pretty good at it through this lesson.
How's this room going? Pretty good.
Hold on 1 second, guys. I gotta go look at through some of my notes and eat some food. I'll be back.
Hello. Sorry. Yeah, it's nothing much. Nothing much. Oh, John, I'm 1600 on chess.com. I'm at 97 point something percentile for it. Mm-hmm. No. You don't really get titles unless you compete like in like FIDE rated tournaments. Yeah. Yeah, it's something light though. Yeah, like a year ago. I started it like in 2021, but I didn't really even know what castling was, and I think I played like 2 games and then quit. So I don't really count that. Like I don't even know what castling was. Mm, all right. Mm-hmm. Hey, I got you, John. I feel you. Oh shoot, a fan base? What? Oh shoot. German was mid. I'm sorry. I hate to tell you. Okay. I just don't find him enjoyable. You know who's a better YouTuber than both than Germa? I don't know who that is. Hikaru Nakamura. Ah. No, you know who's a better YouTuber than um Germa? Heimler. Oh, they can?
Hey guys, I'm back. What's up? I got my friend Caffin with me. He's taking
Yo,
AB Calc AB. Anyway, we got the calc exam tomorrow.
it's so over.
It's not over. It's not over.
So yeah, so I got the 4 on the practice test, but I did so bad on the non-calculator FRQs because like the amount of questions, it's like 4 questions. It's crazy with 60 minutes.
For FRQ. Oh, 4 FRQs? Dang.
Well, because on the calculator one, which I always do good on, like I can always pretty much get like max points on the calculator one.
Yeah.
But the non-calculator, I'm just terrible at.
No,
I
I
don't know
feel
what
that.
it is.
But we have got to go over some FRQs. Once I finish this, because
Oh,
what's the one thing you sent me? Like you said the Orta Cage College Board FRQs?
oh yeah. So on College Board, they have actually like the actual FRQs, like the last 3 years, and they have the scoring guidelines too. We could do
Oh,
those.
that's huge. That's huge. We got to do it.
Yeah. So I'm thinking if we time ourselves and then we like compare what we got and then whatever we did wrong,
Mm-hmm.
we know.
Yeah, I hope they have the scoring, because FRQs, the scoring is really weird. You don't have to have the right answer, as long as you have like the right process to get the answer, you know? You get points for like every little thing, not just the answer. Alright, that's a bet though. Alright, Kevin. Alright, hold on 1 second, folks. Alright guys, let's get back to the video and continue this problem. Let's actually try to solve this before he does. So let's see. We have 1 over n squared converges. And then let's set our limit. Alright, let's go ahead and go back on. Okay, let's start our limit. So I'm gonna write down on paper. I'm just gonna tell you when I'm writing. So the limit as n approaches infinity of 1 over 5n squared. And I'm just gonna leave it as that because the rest of it doesn't really matter right now. And then we're gonna multiply it by n squared over 1. It's gonna give us n squared to cancel out. And we're going to get 1 over 5. So that is a finite number, which means that that must converge. Let's see what he gets.
So now let's set up our limit. So let's just rewrite this whole thing. And then we're going to multiply it by the reciprocal of the one we're comparing it to. So there we go. And now you can see here, what is this limit going to equal? Well, we're going to have the n squared on top, a 5n squared on bottom. None of this stuff matters because we're going to infinity, so it's just 1/5. So 1/5 is positive.
Let's go.
The limit exists. So therefore, they both do the same thing, which was converges. So these, the
so
answer to
L
this
has
is
to be
this
positive.
series
That's another thing I
converges
forgot.
because
L
we
has to
did
be
the
positive.
limit comparison test. All right, another one. So for this one, what do we want to compare? So you look at the largest term, which in this case is this square root of 3n. Whenever we have the coefficients, they really don't matter for when we're comparing, so I can just get rid of that. So I'm going to compare it to, this would be like my quote-unquote reduced.
Okay, my mic was off. Let me do that again. So we get 1 over
The square root
square
of
root
n.
of n, and n is a p series. N is to the 1/2, meaning it diverges. So this is probably going to diverge. Let's see what he gets.
Now, does this thing, I'm going to compare it to this, but does this thing diverge or converge? This is also a
Unless L is negative, in which case we can't tell, but my bet's on diverge.
P series, but in this case, the P, this is n raised to the 1/2, so it's in between, it's less than 1, so it's in between 0 and 1, so therefore this is diverging. So it diverges. So when we do our limit, now if we get our limit, then we know that this thing also diverges. But let's find out first. So our limit, n is going to approach infinity, of this thing, multiplied by the reciprocal of the one that we're comparing it to. And then so you're going to get, as you go to infinity, you have to think, what is this that we have? The leading coefficients, since the degrees are the same, this is just going to be 1 over square root of 3. All right, so since that's finite and positive, then the answer is that they both diverge. So this series diverges. All right, this one, let's compare. Let's see, we have this term and this term. Those are our leading terms. So if we try to reduce those,
let's go ahead and work through this.
Compare it to 1 over, and the numbers,
let's go and work through. It's going to be 1 over n squared because you just minus that. That converges because it's a p series, and n squared, it's greater than 1. So my bet's on
coefficients. We don't care about those, so we just think about 1 over n squared. This is a p series that not diverges, it converges, because the p series, you have p that is larger than 1, the exponent there. So let's check with the limit now. So we take the limit as n approaches infinity of this whole thing, and then we multiply it by the reciprocal of the one we're comparing it to, so n squared over 1. And then you can see here that this simplifies down. Now I'm going to say that it's n to the 5th minus blah, 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 because the other stuff doesn't matter, all over, and then on bottom I have 2n to the 5th plus blah, blah, blah. None of that stuff matters because I'm just going to infinity. So then this equals 1/2. Okay, so we have 1/2, which means since it is the limit that's positive, therefore they both are doing the same thing, so it converges. See, I like the limit comparison test because it's kind of nice. You don't have to figure out which one's larger or not. Okay, so just 2 more examples. I'm doing so many because there's just so many different types that you might be faced with, and I wanted to give you a good feel for what you're going to be faced with. All right, so this one, now we have something crazy going on. So we have this term here.
Okay, let's try to do this. This looks really hard. Let's see. So we have on the top, we have n, 3 to the n. I don't think we can do anything with that because it's all n. Let's go over 4n cubed. That's interesting. What can we do with that? Okay, I give up. Let's see what he does.
This is one term, and we're comparing it with this term. So when we quote-unquote try to reduce this, what are we comparing? So one of those n's would cancel, and we're left with 3 raised to the n over. Yeah, I forgot you can do that. And now again, I don't have to do a coefficient. I can just leave the 4 off and just say n squared, because that one of those n's canceled. So this is what I'm comparing it to. Now, what does this do? Does this converge? Does it diverge? Because we have to figure that out before we start working through. Because if we do the limit and we find out that we find the limit, but that doesn't tell us anything unless we know what this does. So this one's a little bit trickier, but if you remember the nth term test, do you remember that? The nth term test, if you take the limit of this as n approaches infinity, so I'm going to do the limit of the whole thing, and that does not equal 0. When the limit does not equal 0, it guarantees to diverge. If it equaled 0, that doesn't mean it converges. That's the nth term test. The nth term test, we're just going to go off to infinity. If it doesn't equal 0, which in this case it wouldn't, this thing's growing faster than the one on bottom, so then therefore we know for sure it diverges. So now we can use the limit comparison and set up the original one, this whole thing, and multiply it by the reciprocal of the one we're comparing. So in this case, it'd be n squared over 3 to the n. So now I have the limit, n approaches infinity, and then I can see here that that 3 to the n and that 3 to the n are going to cancel, and I end up with an n cubed on top, 4n cubed plus 2 on bottom, and that will equal 1/4. So I have a finite answer. It is positive. Therefore, these are both going to do the same thing. They both are going to diverge. So this series diverges.
We got that.
Whew. All right, last one. Let's compare this one to, okay, so I'm going to look at this n and this. So here's what I'm thinking. I'm going to take n to the first power and subtract the exponent of this. So that is 3. It's the square root, so it's 3 halves. So 1 minus 3 halves equals n to the 1/2. negative 1/2. Yeah, negative 1/2. All right, so I'm going to compare it to 1 over n to the 1/2. That's what I'm comparing it to. Okay, so it's like let's compare this one to, okay, so I'm going to look at this n and this. So here's what I'm thinking. I'm going to take n to the first power and subtract the exponent of this. So that is 3, it's the square root, so it's 3 halves.
Oh,
so 1 minus 3 halves equals n to the 1
3
half.
over 2, so
Negative
1 minus
1/2.
1 over 2 because you're
Yeah,
dividing.
negative 1/2. All right, so I'm going to compare it to 1 over n to the 1/2. That's what I'm comparing it to. Okay, so it's like I simplified the terms that are the largest terms. Okay, so now this is a p-series, because we have to know if this diverges or converges. This is a p-series where the p is less than 1. It's in between 0 and 1. So this is going to diverge. So now let's figure out if this one also diverges. They both diverge if the limit is finite and positive. So we'll take the limit, n is going to approach infinity of this original. We then multiply it by the reciprocal here. Then this cleans up to be n approaches infinity of. So this is now n to the 3 halves on top here. And on bottom, we have still the square root of n cubed plus n. Well, now this part of it doesn't really matter, right? That doesn't really matter. We just have this. These are the same thing. N to the 3 halves is the same thing as the square root of n cubed.
Oh, bet.
So this equals 1.
Which is, so it diverges.
As you go off to infinity. Therefore, they are both doing the same thing, which was diverging. So we say that this one also diverges. So you have to know if one of them's larger than the other, which was just the comparison test, which is where you have to know if one of them's larger than the other, and then that tells you the information. So here's the examples we just covered on that. So make sure the difference between the comparison test versus when we do the limit comparison test. I like the limit comparison test, but sometimes the questions are asked in a way where you have to know this information. You'll see some of those, especially on the test prep section of this packet. So this is Mr. Bean signing off. Rock that mastery check, and I'll see you back in our next lesson.
All right, next unit. Let's go. Got to speed through this.
Hello, Calc kids. Welcome back to another lesson in calculus. This is Mr. Bean. Today's lesson is on something called alternating series. So we're going to look at the alternating series test to help us know if the series is converging or not. Now, an alternating series is when you go from positive to negative, positive to negative. So the first number might be positive, the next number is negative, the next number is positive, and usually what you have here is this -1 raised to the some power, some nth power. Now, it's not always. I'll show you an example later on that you have an alternating series where that doesn't exist, but typically that's what you'll see for an alternating series. So what we get is some kind of like a function here that we say is positive. So if a of n is positive, that's this thing, and you're multiplying it by an alternating number, so positive, negative, this portion of it is the alternating piece, then it's going to converge if two conditions are met. So again, the first thing is we recognize it's alternating, and then if it's an alternating series, then here's the two conditions. The first one is that the limit, as n approaches infinity, of this a of n here, this function, is going to equal 0. That's the first condition. If the limit doesn't equal 0, then it's not going to, well, we can't say that it converges. Now, the second condition here is this, and that is that the succeeding term is smaller than the previous term. So in other words, if you have the first term, the second term will be smaller. If you have the third term, the fourth term is going to be smaller, the one that comes next. Or in other words, this is just a fancy way of saying that it is decreasing, that these things are decreasing. Now, why the absolute value? I put the absolute value there just to make sure that you understand, like we're not confusing it with the negative. Like sometimes students will apply the negative one. Technically, I don't need to put those absolute values there because I've already said here that it's got to be positive, but I'm putting them there. A lot of times you'll see textbooks do that just to reference that it's the entire thing. So we don't care that it's positive or negative. You just take the absolute value and the next term has to be smaller than the previous term after that. Okay, so now how can you check to make sure that it's decreasing? How do you know that a of n is decreasing? One way is you take the first derivative, see if the first derivative is negative. I don't like this way because this is the hardest, most cumbersome part of doing it. So I would probably avoid that if I can, taking the first derivative to see if it's negative. Usually it's obvious. You'll see what I mean, and that is just that if you look at the value of your a of n, the expression, you can just plug in numbers and see, yeah, it's going to get smaller. And then another way is to manipulate this thing. So if we say that the succeeding term is smaller than the previous term, another way of looking at that is one of these two things. You could just say, well, okay, so the bigger term minus the smaller term has to be positive. Okay, that's kind of like a no-brainer. The bigger term minus the smaller term is positive. Or this, I like this one. The first term is the denominator of the second term, or the fourth term is the denominator of the fifth term. And if you create a ratio, that has to be less than 1. That's the only way for that to work out. For these two things to be true, this fraction would have to be smaller than 1. So I'll do one example of those in these notes here. All right, so get those written down. Let's practice this. So with our first example, we have here an alternating series. We have -1 raised to the nth power, so it's going to be alternating. And so let's check to see our various conditions. Now this actually here, this is kind of cool. This we've looked at before. This is harmonic. Okay, so this is our A of n, and this one actually is our harmonic P series. We've talked about this. This is called an alternating harmonic. So a harmonics P series diverges. That part of it diverges. Interestingly, when you create an alternating harmonic, it's going to converge instead of diverge. So here's how we can show that. The limit, do that in blue, the limit as n approaches infinity of 1 over n, so that is going to equal, well, as n gets really, really large, that's just going to equal 0. Okay, so good. Our first condition was met. Check. We're good there. So now our second condition. Is it decreasing? Is it getting smaller? So one way of checking that is just if I look at, this one's the obvious one. If I just say, if I plug in a 1, plus, now plug in a 2, plus, now plug in a 3, plus, now plug in a 4, and so forth. You just keep going and going and going. You can see each one of these numbers is getting smaller, 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 smaller. So yeah, this thing is decreasing. So it meets both conditions. It is alternating. So we can therefore say that it converges by the alternating series test. Okay, so we met both conditions. It wasn't alternating, and so therefore it converges. Okay, so let's try another one here. So this time we have this piece right here. That is our A of n. It is alternating. We have this -1 raised to a power. Now, just because it says n plus 1, that doesn't really change much, except for it's going to start off positive. See, this one started off as a negative number. You plug in a 1, it's negative. This one, when you plug in the 1 there, 1 plus 1 is 2, it's going to make that positive. So that's the difference. When you have an n plus 1, it just makes it so the first number, whether it's positive or negative. That's how it changes things there. So let's first do the limit. First condition. So I'm just going to write A of n here, A sub n, because I don't want to rewrite that whole thing. So that is going to equal, well, let's see. This is an n to the first power. This is going to have an n squared on bottom. So an n squared on bottom with an n on top is going to make this thing approach 0. Okay, so we're good there. First condition met. Now what about the second condition? This is where it gets a little tricky. So we could do this thing where I plugged in numbers and I just kept going and going and going, and I could show a whole bunch of numbers there. And if I was using a calculator, that's kind of a nice thing. I could just plug this into the calculator and check the table. I like using the table function and check for the table of values. But let me show you this trick here, which was dealing with this one. So I already know what A of n is. Let's write down what A of n plus 1 is equal to. So if this n becomes an n plus 1, that makes this n plus 6. N plus 1 plus 5 is n plus 6. This one is n plus 1 plus 2. That's just n plus 3. This n plus 3 now becomes n plus 1 plus 3. So it's now n plus 4. So what next? Now we're going to do the ratio. So remember the ratio was that I'm going to say A of n plus 1 divided by A of n. So I'm going to take my A of n plus 1. So I'm going to rewrite this down here real quick. N plus 6 over n plus 3 times n plus 4. And now instead of dividing by A of n, I'm going to multiply its reciprocal. So the reciprocal of this, n plus 2 on top times n plus 3. And that's all over n plus 5. So now let's see, is this thing less than 1? Well, that's really, like, how do I know that? I'll show you. We're going to cancel out the n plus 3, cancel out the n plus 3. And then I'm going to multiply out long way. So I'm going to take n plus 6 times n plus 2, multiply that out, and I get n squared plus 8n plus 12. And then all over, and now I'm going to multiply n plus 4 times n plus 5. That gives me this here, n squared plus 9n plus 20. Now, how do you tell if this is actually less than 0? Or excuse me, less than 1, I mean. I'm going to leave this numerator alone, n squared plus 8n plus 12. Now, this is kind of a cool way to manipulate this. If you take this, this is the same thing as n squared plus 8n plus 12. It's going to, I'm going to write it exactly like the numerator, But then, so I have this portion of it plus, so look here, I can say 1n plus 8. See, that is all equivalent to this denominator. So you can see here, the denominator is the same as the numerator plus a little extra, plus an n plus 8. So that's how you can say that, yes, this is less than 1. So it meets both conditions, and you can say that this converges. Okay, so that was a little
It's less than 1 because the denominator is greater. Okay, makes sense.
bit complicated, but it is a way that you can prove and show how it is a decreasing function there. Okay, number 3, this here, yes, again, it's alternating, -1 raised to the n plus 1. So now what's my a of n? My a of n, that I'm going to check the limit as n approaches infinity. This one is n plus 7 over n. That was sloppy. Let me clean that up. There, that's better. So now what does this equal? This is equal to 1. You have to know your horizontal asymptotes, right? We're going off to infinity. This is the first power. This is the first power. The leading coefficients are 1. So this equals 1. That does not equal 0. So therefore, we can stop. We don't even need to check the second condition that it's decreasing or not. Because whether it is or not, it doesn't matter. It does not meet this condition. Therefore, this thing is going to diverge. And we're done. So it diverges. In fact, if you remember the nth term test, if the limit doesn't equal 0, then we know it diverges. If it doesn't equal 0, we'd check the second condition. But once one of the conditions doesn't work, you're done. You don't have to check the other one. Okay, this one here, number 4. So when you first look at this one, this is an example of where we don't see this -1 raised to the nth power. So when you don't see it, sometimes we think, okay, this must not be alternating then, and so how we might approach this differently. But this is an alternating sequence. And the reason is because cosine of 1 pi equals -1. And then if we plug in a 2, cosine of 2 pi equals +1. And then cosine of 3 pi equals -1 again. And it's going to bounce back and forth from -1 to 1, -1 to 1, over and over again. So this right here is the alternating piece. The cosine is the alternating. So since it's alternating, we can go ahead and check our 2 conditions. So we'll go ahead and do the limit as n approaches infinity of the a of n. A of n is 1 over n, which we already did this one, right? That was back on example number 1. We did the 1 of n. So it's actually the same problem as number 1, if you recognize it, but it's with, but now the alternating piece looks a little different. So we said this was 0, so that meets the first condition. And then we know that 1 over n decreases.
I really am just watching
it's decreasing. And so we can go ahead and say that this converges by the alternating series
I wonder if I'm
test.
allowed to do this.
Okay, so you can see this isn't too bad. Let's do
Just
one
imagine.
more example here, and that is you have one.
Wait,
say that this
can. Okay, alternates because of cosine. I wasn't really paying attention, but 1 over n is, yeah, it's 0. 1 over n is decreasing. 1 over n decreasing. Yeah, because of 1 over 1, 1 over 2, 1 over 3. So this n pi doesn't even matter. Okay. Hey, Catherine. All right, guys. So I hope that you learned a lot today. Um, I'm gonna go study on my own.
Guys,
I realize that
he's
this is
keeping me hostage.
what? No, no, I'm not. No, 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 no. Don't listen to him. He's not. Don't worry about that. Um, I'm gonna go study on my own and then take some breaks. But I hope this is good. I have to work through the rest of this. I hope y'all probably studied a lot more than I did. I don't even know Taylor's series yet. Anyway, it's been fun.
Oh,
Good luck on the BC test. Yeah, don't worry about that. Good luck on the BC test. Bye bye. Have a good one. Subscribe, all that good stuff.